In this video, I'll be going through my notes on Level 3 electrical systems. A link to the PDF and a list of corrections are in the video description. Direct current. Current is the flow rate of charge measured in amperes. As an equation, our current symbolized by I is equal to the charge divided by the time. Conventional current direction is defined as the direction of positive charge flow, opposite the direction of negative electron flow. So if we have our electrons traveling in one direction, we define our current to be in the opposite direction. Changes in current travel at 3 × 10⁸ meters per second, or in other words, the speed of light. Electrons themselves only travel at millimeters per minute. To explain why this is, consider opening the tap on a hosepipe. Although it may take several seconds for an individual particle to travel through the hose, if the hose is pre-filled, water will flow from the end almost immediately. Voltage. Voltage is the energy lost or gained per charge between points in an electric field. We measure it in volts. As an equation, our voltage is equal to the energy divided by the charge. The voltage across the lamp below is 12 volts. This means each coulomb of charge delivers 12 joules of energy. Ohm's law. Charges moving through a conductor encounter resistance. The amount depends on the shape and structure of the material. We measure it in ohms. When a voltage is applied, the resulting current is limited by the resistance. This relationship is called Ohm's law. The equation is that the voltage is equal to the current multiplied by the resistance. For the same amount of voltage, an increase in resistance will result in a decrease in current. In an example, if we have a 12 volt source and a 6 ohm resistor, our voltage of 12 and our resistance of 6 must result in a current of 2. Here I have a section of wire suspended between 2 retort stands. I have bits of paper draped along the wire to better see its motion. When a voltage is applied, we see the wire sag. This happens because as the voltage is applied, current flows through the wire. Due to the wire's electrical resistance, the wire heats up. As it heats up, the metal expands and the wire droops. Equivalent resistance. Multiple resistances in a circuit can be combined into a single equivalent resistance. This equivalent resistance depends on the configuration of the resistors. For resistors in series, the resistances are added together. In this configuration, adding resistors increases the resistance. For resistors in parallel, our 1/over resistance is the sum of the 1/over resistances, which means that in this configuration, adding resistors decreases the resistance. The key point here is not that we're adding resistance, it is that we are adding pathways. And even if those additional pathways have a high resistance, they still allow more current to flow. In this experiment, we're going to see what happens when we combine bulbs in series versus when we combine them in parallel. Starting with one bulb, we get a current of roughly 320 milliamps. Adding a second bulb, we see the brightness decrease, and the current reduced to roughly 250 milliamps. With a third bulb, our current reduces further to 205, and our bulbs are significantly dimmer. Repeating this for our parallel circuit, with one bulb, we see a current of 0.34. Adding a second bulb, we get a current of 0.72. And with 3 bulbs, our needle goes off the scale. To summarize these experiments, adding bulbs in series increases the resistance and reduces the current. This happens because the bulbs share a single pathway, and each added bulb increases the resistance of that pathway. For our parallel circuit, it was the other way around. For each added bulb, the resistance decreased and the current increased. This happens because each added bulb is added on its own pathway, with a resistance and current that is independent to the others. And so our total current increases because there's more pathways through which it can flow. Internal resistance. Voltage sources contribute to the resistance in a circuit due to their own internal resistance. We can therefore represent a power source as an electromotive force, symbolized by epsilon, and resistor in series. When a current flows, the voltage consumed by the internal resistance is IR. Recalling that Ohm's law tells us V equals IR, we can therefore write the overall terminal voltage as this equation here. Our terminal voltage is the electromotive force minus the voltage subtracted by the internal resistance, which is IR. Capacitors. Capacitors store energy in electric fields, as opposed to batteries which use chemistry. Two common types of capacitors are electrolytic and ceramic. In this course, however, we're mostly only going to be looking at parallel plate capacitors, due to the fact that they're as simple as a capacitor can get. Capacitors are able to charge and discharge much quicker than batteries, but have less capacity. Capacitor capacity is called capacitance, measured in farads. Specifically, capacitance is the charge stored per volt applied. As an equation, the capacitance is the charge divided by the voltage. Here I have a bar of aluminium and an ultracapacitor. This is a capacitor with a low voltage, meaning that I can place my hand across the terminals and no current will flow. But what it does have is a very high capacitance, and therefore the ability to create a very high current flow. Dielectrics in capacitors. A dielectric is an electric insulator that allows the separation of charges within itself, via which electric energy can be stored. Dielectrics are used in capacitors to physically separate the opposing plates and increase capacitance. So if we have our parallel plate capacitor here with our positive plate and our negative plate, we can place a dielectric substance in between, and the resulting electric field stretches those charges apart. The negative charges attract to the positive and the positive to the negative, almost like storing energy by stretching a rubber band. The effectiveness of a dielectric is described by its relative permittivity. And here I have a list of common materials and their relative permittivities. The permittivity in a vacuum is 1, and for air it's close enough that we also assume it to be 1. The capacitance of a capacitor can be increased by increasing plate area, which makes more room for charges, decreasing the separation, since less distance means a stronger attraction, and increasing the permittivity, which results in more separable charges. The equation for our capacitance is equal to our permittivity, which is the vacuum permittivity, multiplied by the relative permittivity, multiplied by the area of the plates, and divided by the plate separation. Charging and discharging capacitors. The charging and discharging of capacitors follow an exponential curve. We further quantify this by defining the time for a 63% change as the time constant tau, where our time constant is equal to the resistance multiplied by the capacitance. For a charging capacitor, we can visualize this on a voltage time and current time graph, where as our capacitor charges, our voltage increases, and after a 63% change, we have reached our time constant tau. Our current starts off initially high, but then the current slows as the increasing capacitor plate charge increasingly repels new incoming charges. After a 63% change, we have once again reached our time constant. For a discharging capacitor, we can once again visualize this on a voltage time and current time graph, where in this case our capacitor is initially charged, so the voltage is initially at maximum, and then decreases to 0, and at the point of a 63% change, we have of course reached our time constant. As for our current, the current is initially high as the plate charges repel each other from the charge-dense capacitor plates. And once again, the time for a 63% change is our time constant. Note that the graphs of current for both cases are the same, whereas for voltage they're inversed. Energy in a capacitor. When charging a capacitor, the energy supplied is equal to the charge times the voltage, which since charge is C times V, we can also write as CV squared. Half the energy supplied is lost to the resistance, which is a fact that might seem initially surprising. So why is that the case? As the capacitor charges, the current decreases from its maximum value to 0. Because resistor voltage is proportional, it does too. What I mean by this is that the voltage in our resistor is the current times the resistance, and so the current in the circuit is directly tied to the voltage in the resistor. And so our current decreases as our capacitor charge increases, and so too does our resistor voltage. The area under this graph is the energy lost to the resistor. The capacitor voltage increases in proportion to the decreasing resistor voltage. One way to think of this is that our total voltage of our supply must equal the sum of our resistor voltage and our capacitor voltage. So that if our source voltage is 12, if one is 0, the other must be 12, and vice versa. And so our capacitor voltage increases as our capacitor charge increases. And similar to before, the energy under this graph is the energy stored in the capacitor. As you can see from the shapes of these graphs, the overall voltage supplied is split between the resistor and capacitor. As voltage is energy per charge, the energy supplied is also split. Where hopefully you can see that we could take this area, flip it around, and place it exactly in here. This resistor energy plus our capacitor energy is our total charge Q multiplied by our total voltage V, or in other words, the total energy supplied. And so the energy stored in the capacitor is half our total energy, half of QV, which, as we know, QV can also be written as CV squared, is half CV squared, which is the equation you'll get on your formula sheet. Capacitors in circuits. As with resistors, we can replace multiple capacitors with a single equivalent. For capacitors in series, our 1 over capacitance is the sum of our 1 over capacitances. For capacitors in parallel, our capacitances are summed together. You might note that this is opposite for resistors. Magnetic flux. We can describe the amount of magnetic field passing through a surface as magnetic flux. It has units of Webers. Maximum flux occurs when the field is perpendicular to the area, as we see it is here. Our equation for our magnetic flux is just our magnetic field multiplied by the area. If the field is instead at an angle to the perpendicular, the flux is reduced, and so we see our field lines intersecting our surface at an angle theta. Our magnetic flux then becomes our magnetic field times our area, but now multiplied by cosine of the angle. Faraday's law. Changes in magnetic flux induce EMFs or voltages equal to the rate of change. As an equation, our induced EMF is equal to negative the change in magnetic flux divided by the duration over which it changed. The negative sign indicates that the induced EMF is in opposition to the changing flux, similar to the negative in Hooke's law. Visualizing our flux and EMF on a graph of time, we see that when our lines are not intersecting our area, we have a flux of 0, and when they are perpendicular, we have a maximum flux, and so on. Our induced EMF is equal to the rate of this change. The maximum rate of change occurs when our flux is at 0, similar to how a pendulum's maximum velocity occurs when it is traveling through equilibrium, giving us this following pattern. Lenz's law. When a coil of wire or a solenoid experiences a changing magnetic field, a current is induced in opposition to the change. And so if we bring the north pole towards a coil of wire, a current is induced in our wire, establishing a north pole itself, which repels the incoming north pole. A handy way to remember this is to draw an N and put arrows on the ends, and that gives you the direction of the current, which in this case is an anti-clockwise current. For a south pole moving towards, we can use a similar trick, drawing an S and putting arrows on the ends, which indicates a clockwise current. If we were instead moving the magnet away, these situations are reversed. Note that this effect is only present while the magnetic flux is changing, which is only the case while the magnet is in motion. Here I have two plastic rollers, a thick bar of copper, a disc that isn't magnetic, and a disc that is. Waving the non-magnetic disc above the plate has no effect, whereas the magnetic disc produces a non-contact force. Because copper isn't magnetic, this effect must be partly electric. What's happening is that as the magnet passes the copper is experiencing a changing magnetic field. This changing magnetic field produces an electric current. This current produces a magnetic field, which interacts with the original magnetic field of the magnet, producing a repulsive force between them. With another copper plate, we can perform a variation on this experiment. The non-magnetic disk falls without intervention, whereas the magnetic disk is slowed in its descent. Kirchoff's current law. The total current entering a node must equal the total current exiting that node, or in other words, the current in must equal the current out. In a sense, this is just conservation of energy. As an example, if we have 12 amps and 3 amps entering, our total current entering is 12 plus 3, which is 15, which means we must have the same 15 amps exiting, which could, for example, be achieved by 7 amps plus 8 amps. Kirchoff's voltage law. All the voltages in a circuit loop sum to 0, where voltage sources add voltage and resistors subtract. There are a few exceptions to this, which I'm going to attempt to demonstrate in the example below. If we have a circuit with a 6-volt source going through a resistor, which is taking away 2 volts, leading to another voltage source, and with a parallel resistor in between, we can imagine 3 loops. This loop here, loop 1, this loop here, loop 2, and the outside loop, loop 3. Let's describe our loop 1. Starting at our 6-volt source and moving clockwise, which is an arbitrary decision. You can start anywhere and move counterclockwise if you wanted. You might see that I've started with a negative 6 volts, which contradicts my statement that voltage sources add voltage. The reason this is negative is that this voltage source opposes the current, so it is negative. So our current moves this way, as indicated by the arrows, and because our positive plate is on this side rather than the other, it is repelling our positive current, meaning that our voltage must subtract. This is one of the catches. Continuing around, we have our resistor, which subtracts our 2 volts. Continuing further, we reach our resistor of 8 volts, and whereas usually our resistors subtract, in this case the current is in the opposite direction, so this becomes positive. Completing our loop, minus 6 minus 2 plus 8 does indeed equal 0. Let's now look at our loop 2. Starting off with our 8 volts, moving around clockwise once again, we reach our 8 volt resistor which subtracts 8 volts, and then we bring ourselves full circle, which means that our 8 minus 8 is equal to 0. For our final loop 3, we're going to start at our bottom 8 volts, and moving around clockwise, we reach our voltage source, which is once again opposing the current, so it's negative. Continuing on, we reach our 2 volt resistor, which because it is a resistor subtracts our 2 volts, meaning that our 8 volts minus 6 volts minus 2 volts must equal 0, and the arithmetic seems to work out. Self-inductance. Self-inductance describes how effectively a conductor induces a back EMF in itself. We measure inductance in units of Henry. You may be wondering, how can a conductor oppose changes in itself? Imagine the situation where the current changes in a conductor, for example a low current to a high current. This causes a changing magnetic flux in itself as the magnetic field grows or shrinks. In the illustrated example, we have the current increasing, and so the flux is growing. As a result of our changing magnetic flux, our inductor is inducing a back EMF in itself, opposing the original current change, as we see here. And so just to recap, we have a current changing, resulting in a changing magnetic flux, which induces a back EMF that opposes the original current change. And note that the diagram shows an increasing scenario. For a decrease, the current and flux instead reduce, and the EMF is reversed. Inductors. An inductor is a component that is designed to have a particular self-inductance. Here are some common circuit examples. Due to this self-inductance, inductors produce a back EMF in opposition to current changes in their circuit, slowing these changes. If the current through the inductor is constant, no back EMF is produced, and the symbol for an inductor is this one here. Let's now look at a graph of current versus time and of our EMF versus time. Initially our current is 0, so we have no EMF, and then our current increases. While our current is increasing, we have a back EMF. Our current then reaches a steady state, which means it isn't changing, meaning that we have no back EMF. Our current then decreases to 0, and because it is once again changing, we once again have a back EMF. Because the change is the same but takes twice as long, our rate of change is halved, and so too is our back EMF. Inductive factors. The inductance of an inductor is increased by several factors. Starting with our original inductor, the first thing we can do is to add more coils. This increases the inductance because there are more coils interacting with the magnetic flux. We could add more area. More area requires more coil, more interaction with the magnetic flux. We could make our windings tighter. In doing so, the coils are more closely affected by each other's magnetic flux. And we could also add a core, which allows the magnetic flux to conduct with less losses. Inductor energy. While current flows through an inductor, it stores energy in the form of its magnetic field. More current means a stronger field, which means a higher energy. The equation that describes this is that the inductor energy is equal to half the inductance multiplied by the current squared. Inductor time constant. Similar to a capacitor, the current and voltage change in an inductor follow an exponential curve. We can once again define the time for a 63% change as the time constant tau, where in this case our time constant is the inductance divided by the resistance. For a charging inductor, we can consider our voltage time graph and our current time graph. Initially, the current increases rapidly, as we see here, causing a large opposing voltage, and we see our voltage is indeed at its maximum. Over time, the current reaches a steady state, meaning that the rate of current change reduces, meaning that our back EMF, our voltage, also reduces. And once again, the time for a 63% change is our time constant. For a discharging inductor, initially current decreases rapidly, as we see it doing here, causing a large opposing voltage. And so our large rate of change results in a large voltage or large EMF. As the rate of change of current slows down as it reaches a value of 0, so too does our back EMF. And once again, the time for a 63% change is our time constant tau. Transformers. A transformer consists of two inductors, arranged such that the flux change in one produces a near equivalent flux change in the other. This is called mutual inductance. Here is a diagram of a common transformer, where we have a primary coil, across which we have the voltage Vp, and the number of turns or number of loops, Np. We also have our secondary coil, the voltage across which is Vs, and the number of turns is Ns. A core of iron is often used to improve flux transmission. The iron is laminated to reduce eddy currents, which cause energy losses. And so if our core was not laminated, we would be producing very large eddy currents, which would result in large energy losses. With these laminations, we're able to reduce the size of these currents. Transformers are often used to increase voltage at the expense of current, or vice versa. This is dependent on the turn ratio. The turn ratio is the ratio of the primary turns to the secondary turns. This is equal to our primary voltage divided by our secondary voltage, which is equal to the secondary current divided by the primary current.
This here is a Jacob's ladder. This consists of a pair of wires that are closest near the bottom and further apart at the top. When a high voltage is applied between the wires, the air is ionized and an electrical pathway is formed. Due to its high temperature, this ionized pathway rises and lengthens as the wires move further apart. Eventually, the resistance of this pathway is great enough that it's more energetically favorable to ionize a fresh path.
AC circuits. Whereas a direct current DC flows in a single unchanging direction, alternating current AC alternates direction. Direct current on a current time graph appears as a steady unchanging value, whereas for alternating current, the current goes back and forward. Both voltage and current follow a sinusoidal relationship. As equations, our voltage is equal to the maximum voltage multiplied by the sine of our angular frequency and our time, whereas the current is equal to the maximum current, once again multiplied by the sine of our angular frequency and our time. Why this term omega t? Consider that our omega is just our angle over time. This equation is on your formula sheet. If we multiply both sides by t, we wind up with the angle is equal to omega t. And so omega t is just another way of writing the angle. We use it because it's often more convenient, as you'll see over the next few pages. RMS. The voltage and current in an AC circuit are changing constantly. It would be useful to describe AC voltage and current with a constant average value. Trouble is, this is always 0. We instead take the square root of the mean voltage or current squared, or RMS. And so on our graph, you can see that when we have a sinusoidal relationship, our average value is 0. For a better average, we take our negative values and put them up here, which we do by squaring and square rooting, where our peak is up here. And then we take the average, or in other words, the mean. If you work through the mathematics, which we don't need to do here, you arrive at the voltage RMS is equal to the root 2 times the voltage peak, and likewise for the current. Multiplying VRMS and IRMS provides us with the same power value as an equivalent DC circuit. LCR circuits. An LCR circuit consists of an inductor, capacitor, and resistor. This forms a resonant circuit where energy oscillates between inductor and capacitor. Here is a circuit here with our inductor L, capacitor C, and resistor R. Energy is stored in the capacitor in the form of the electric field. It is at its maximum when the current is equal to 0. Recall that our current is 0 when our capacitor is fully charged. Energy in the inductor is stored in its magnetic field. This is established when the current increases and collapses when the current decreases. It is at its maximum when the current is at its maximum. Let's now go through the phases of an LCR circuit. Let's start with our LCR circuit with our capacitor fully charged. In this case, our capacitor energy is at its maximum, and because there is no current flowing through the circuit, our inductor energy is 0. As our capacitor is discharging, we have a current increasing, and due to our inductor, we have a back EMF opposing this increase. Because our capacitor isn't fully discharged, we still have some energy left, and because a current is flowing, we now have some inductor energy. When the capacitor is fully discharged, our current is at a maximum, so we have no energy in our capacitor, and our maximum energy in our inductor. Following this, our current is now decreasing, our back EMF opposes this decrease, and our capacitor starts charging the other way. And so now we have some energy in our capacitor, and because we have a decreased current, we have a decreased inductor energy. Eventually our capacitor becomes charged again, our current comes to a stop, we have all our energy in our capacitor, and none in our inductor. So you might note, throughout this exchange, our capacitor energy went into our inductor, and then back into our capacitor. It's important to note that while we have returned to the same stage in our cycle with a capacitor that is charged, our total energy has decreased from the original energy due to the losses from our resistance. Phase in an LCR. In an LCR circuit with a power source, our inductor voltage leads our resistor voltage by 90 degrees, our capacitor voltage lags the resistor voltage by 90 degrees, and our resistor voltage is in phase with the current. Let's now picture this on a graph. We start with our voltage of our resistor at a negative maximum, which means so too is our current. Because our current is at a maximum, it isn't changing, meaning that we have no voltage produced by our inductor, or in other words, a back EMF. And our capacitor is uncharged, analogous to a pendulum at its equilibrium position, right before it starts to charge again. As our capacitor charges, our current goes to zero, and because our rate of change of current is at its maximum, we have a maximum voltage across our inductor, which, as you might recall, is proportional to our rate of change of current. Our capacitor then discharges and our current increases. As our rate of current change decreases, so too does the voltage across our inductor. Our capacitor then charges in the opposite direction, at which point our current is once again zero, and our voltage across our inductor is a maximum because we have a maximum rate of change of current here. Our capacitor once again discharges, increasing our current, which reaches a point of zero rate of change, resulting in once again zero voltage across our inductor, and so on. Representing that on a counterclockwise rotating phasor, we see our inductor voltage and capacitor voltage with a phase difference of 180 degrees, and our resistor in between, where, as stated above, our VL is leading our VR, and our VC is lagging our VR, keeping in mind that this is rotating in this direction. With this circuit, we can imagine three different situations. The first is where VL is greater than VC. Looking at our phasor diagram, we have our VL upwards being reduced by our smaller VC. Because our Vs is the combination of these two voltages, it points in this direction here. So consider our resistor voltage, add on our inductor voltage, reduce that by our capacitor voltage, and our source voltage must be pointing in this direction. Because our Vs is above our orange resistor voltage, in this case our source voltage is leading our current. In the situation where our inductor voltage is equal to our capacitor voltage, we have our resistor voltage plus our inductor voltage, and then adding on in the opposite direction our capacitor voltage, which is the same size. This results in a source voltage, which is in phase with our circuit current. Lastly, if our inductor voltage is less than our capacitor voltage, we have our resistor voltage, adding on our inductor voltage, and then adding on in the opposite direction our capacitor voltage, which is in this case larger. Because of this, our voltage source points downwards, meaning that our source voltage is lagging our current. Reactance. Reactance is the opposition to an AC current, caused by the inductance and capacitance in a circuit. Like resistance, reactance is measured in ohms. Unlike resistance, energy is not lost to reactance, it is stored. Reactance can even be negative and cancel out. The capacitor reactance is given the symbol XC and is equal to 1 over the angular frequency multiplied by the capacitance. Our inductor reactance is given the symbol XL and is equal to our angular frequency multiplied by our inductance. Recall that angular frequency is equal to 2 pi our frequency, so that when we increase the frequency, as you can see from these two equations, our XL increases and our XC decreases. Impedance. We have now learned that current is opposed by both resistance and reactance. Impedance combines these effects into a single term. Our impedance, given the symbol Z, is equal to the square root of our resistance squared plus our reactance squared. Because our inductor reactance and capacitor reactance are in opposite directions, our reactance is equal to XL minus XC, allowing us to make this substitution. Putting these terms into further context, our source voltage is our current times impedance, our resistor voltage is our current times our resistance, inductor voltage is our current times inductor reactance, and capacitor voltage is our current times capacitor reactance. LCR resonance. Recall that XL and XC are inversely dependent on frequency, meaning that given our equations here, if we increase our angular frequency, we would see a reduction in our capacitor reactance and an increase in our inductor reactance. If we reduce our angular frequency, we would see the opposite. On a graph of angular frequency, we see that as we increase frequency, we see an increase in our inductor reactance and a decrease in our capacitor reactance. This means there exists a frequency at which our capacitor reactance is equal to our inductor reactance. This frequency is what we call the resonant frequency. Because our capacitor reactance and inductor reactance are 180 degrees out of phase, they cancel out, and our total reactance is 0, so our X, which is equal to XC minus XL, is equal to 0, which means that our impedance is at a minimum and is equal to our resistance. Mathematically, we have our impedance, which is equal to our our square root of r squared plus x squared. In the case where our reactance is 0, we just get the square root of r squared, which is just r. Because our impedance is at a minimum, our current is at a maximum. And so once again, using a graph of frequency, we have our resonant frequency in the middle. When our frequency is lower, our capacitor reactance dominates. And when our frequency is higher, our inductor reactance dominates. And since Vs is equal to Iz, our current follows an inverse relationship.